Good morning, students. We are discussing about the determination of height of pack tower. And last day we took the differential balance, mass balance for a unique unit cross section pack bed, and DH is the control volume. And from there we turn in this equation, height of a vector equal to, that is y1 by 1 2, that to exit concentration, g dash ty, g dash is the flow rate per unit area, ky mass transfer coefficient, individual mass transfer gas phase, specific surface area 1 minus y into y minus yi. And then we discuss about how to solve this equation numerically. Okay, because here yi is also or depends on the y, because different y value, if you take this y value, then if you take the slope minus kx, wherever you will do, that is your corresponding xi and yi. So for this y value and x value, this is your xi and y. And when you integrate in this one from y2 to y1, so you have to take the different point, and accordingly different xi and yi will be there, and this thing you have to solve numerically. And this line is called the tie line. And then what we have seen that height equal to total this. So this is, if I take this as a function fy, okay, g dash this, and to dy, okay, this is my function. So now if I integrate initial problem, so y2, okay, you start with this. Now you up to go y1, then each point you calculate the function that you calculate with this, because every each y value you will get yi. So accordingly you have to calculate this value. Then if you calculate, then it will be on curve, and then area under this curve will be your height of the column. And this thing we have to solve numerically. That last day we discuss. Now if you see, we have derived this equation taking the gas phase, means mass is transferring from the gas phase to liquid phase, and the whole balance was done from the gas phase point of view. Okay, that's why the things work. Okay. So now if I calculate this one from liquid phase, means considering the liquid phase, okay, liquid phase entering, going, and Lx particular this, and dlx, what we have started here. If you see, we started with that change is g dash y, then this, instead of I can write l dash x and dl dash x. In this way also I can do that way, because how much, whether I'm taking, I made this balance here from gas phase. Now if I make the balance from the liquid phase in the similar fashion, then I will end up with this equation. Instead of ky, it will be kx a, okay, and this 1 minus x into, in this case, y minus yi, that will be xi minus xi for absorption. Okay, and here if you see it, I had this ky, okay, ky. Now if I express in kg, so I know that will be kg into p. That also you can calculate, whatever the unit thing you can calculate. But if you had calculated in ky, then kx a 1 minus x, this will be same. It will be xi minus x. Okay. And if you calculate that C average, okay, then it will be KL A C average 1 minus x into xi minus x L dash dx x2 to x1. This will come like similar. Okay, already we have seen. Now height of the packing for the stepping column will be obtained in similar way, but at that case y2 will be greater than y1. Okay. And the gas phase driving force will be yi minus y. So the then design equation will be this, d dash y1 minus y into yi minus. In this case y minus yi, and stripping case it will be yi minus y, and this limit will change. So you can do it, all this thing similar way calculation, it will come end up with this equation. Now, so still now we have discussed this thing in terms of individual mass transfer. Now, if I express this one in terms of overall mass transfer coefficient design equation. So, what is my DH? DH was individual mass transfer. We know just only change will be capital KY into Y minus Y star in this case, overall mass transfer KY. So that time I wrote Na small ky y minus yi, but here it will be this. So then it will be capital Ky, this change y will be there, and in this case that instead of y minus yi, it will be y minus y star, and then height will be this. So if I express in terms of overall mass transfer coefficient, that only the driving force, this part will change and this part will change. And if you take this in term ky to kg, okay, then only pressure that term will. So this thing, see, one equation, this equation you can experience in different way according to need of your problem, because what either you, there is two ways, either you convert your mass transfer coefficient according to what way you want, or if your mass transfer whatever data you can use the corresponding equation, and these are the simple modifications are required. You can similarly for liquid phase, that for overall mass transfer, that will be instead of small kx, that will be capital Kx, and it will be what xi minus x, instead of this it will be x star minus x, the driving force will be x star minus s. Okay, and this will be that corresponding equation. So but so height of a transfer unit, okay, height of this column for this one according to different mass transfer coefficient, different forms are there. Now you have to handle this way. You can handle in two ways. Either you use one equation for from, or there are so many equations similar, but you use one equation, and what are the mass transfer equation is there, that whatever mass transfer is given to you, so you have to convert this equation, convert this mass transfer as per your need. Let's take, I want to use this equation. Let's take ky a 1 minus y this. If I want to use, so driving force I have to use this, and capital ky I have to use. So whatever data will be given to you, kx, small kx, ky, kg. So accordingly that conversion you have to do, that we have discussed in detail in chapter 3 and 4. Or you can tell whatever data is given to me, that corresponding mass transfer coefficient, and corresponding equation also you can solve, and then you have to make the little bit tricks here. Yeah, but basic is this one, kg dy small ky a 1 minus y minus yr. So this is the driving force. So but if whatever thing you are using, either overall or liquid phase or gas phase, this will change, and corresponding this will also change. Other thing will remain, and this 1 minus y, that will be 1 minus x, the like this. So accordingly you have to change this one in this form. It is there. Now there is one interesting thing is there. Now height of a transfer unit, I got this equation. Let's take y2 minus y1, y2 to y1, g dash dy small ky a 1 minus y into y minus y star. Now if I multiply it into yibm up and down, I can make it even. So y by mean is log mean value of yb. Yb means 1 minus yi. That means it I can ibm. I can tell 1 minus im. So 1 minus im equal to 1 minus I into 1 minus 1 minus y into ln 1 minus yi by 1 by 1. Okay. So this equation, instead of yibm, I can write, instead of 1 minus yim, in this way I can write this one. Now here one interesting thing is there. It has been observed that this g dash ky a bar into 1 minus y ibm, it will it generally it will be fairly constant. Because why? Generally mass transfer coefficient varies with this. If g dash will increase, mass transfer will increase. Okay. Mass transfer will increase means 1 minus im, that will increase. So actually this is increasing, this, and that increment part is in soja, that this term is, it has seen that this term is fairly constant. G dash ky a 1 minus y I. That Kulvar, he has seen this one. So if this is a fairly constant, then I can take this thing in out of integration term. So then that's mean I can take the g dash ky a bar into 1 minus I out of integration, then integration this y2 minus y1 yim dy into this, and this is called HT. HTG is called, HTG is the height of a transfer unit. Height of a transfer unit means single height. What is the height of a transfer unit? This, and this into this, k dash into this is called ky dash. Okay, what is the ky into this? This is called ky. So g dash into ky dash a. So this term is called height of a transfer unit, HTG, based on gas phase. Okay. Height of transfer units based on individual gas phase coefficient, or height of an individual gas phase transfer unit, HTG, because things are determined based on gas phase. Okay. And this integration part, this is called NTG. NTG is number of individual gas phase transfer unit, NTG. So total height equal to what? Height of a single transfer unit into number of transfer unit. Now this is, so this equation just I am dividing into parts. So because this part is constant, and if you see interesting part, HTG is depends on what? Flow rate, ky mass transfer coefficient. A is very important parameter, because if you can increase the specific surface area, height of a single transfer unit will decrease drastically. You understand? Let's take height of it. If you have a what a value, let's take 200 meter square per meter cube. If for that one you have a, let's take height of a transfer unit is 10. Now if you can increase it in, let's take 200 to 800 meter square, then it height of a single transfer unit will be 10 meter by 4, 2.5 meter. And if number of transfer unit is whatever, if it is 2, then 5 meter total. Initially it was 10 plus 2, 20 meter. Now it comes to 2.5 into 2, so 5 meter. So that is the thing. That's why, and it's the characteristics of the packing material. A bar is very important, but G bar, G dash you cannot change much, because G dash will be whatever flow rate it will be given to you, and what will be diameter. It is also for this thing. It is constant, fairly constant. There won't be much change. And one, that flow rate is constant, that mass transfer coefficient, it is also will be some equivalent, because your system is defined, so your mass transfer coefficient also will increase. And this thing y my 1 r, but if it is a dilute solution, then 1 minus y I m, it will be almost equal to 1. So these three parameters are fairly constant for a thing, but here I can change the mass transfer area. That is the condition of the packing material. So this thing we have to see, that it is height of a, and this is the height of a single transfer. A number of transfer unit will come from this integration part, and this is the depends on the particular process. So height of a transfer unit and the number of transfer unit can be defined similarly when any other kind of mass transfer coefficient is used. Instead of this, so here I have determined that total height is height of a transfer unit based on gas phase, number of transfer unit based on gas phase. But if you take the overall and all liquid phase, based on liquid phase or overall, whatever it is possible to calculate. Okay. For example, if the mass transfer is expressed in terms of individual liquid phase mass transfer coefficient, the height of the packing can be written as HTL NTL. So height of transfer based on gas liquid phase. So what is HTL? Then L dash K dash A bar into XIBM, or 1 minus XI. This will be this, and NTG will be 1 minus X IM dx 1 minus X into X minus X. So that equation, okay, that is coming this way. So our HTL is height of an individual transfer liquid phase transfer unit, and number of NTL is number of individual liquid phase transfer unit. Now if I want to express in terms of overall, okay, if the overall gas phase mass transfer coefficient is used to express the rate of mass transfer, the height of a packing material can be obtained the following equation. So then it will be G dash Y IBM star, because capital K1 1 I and Y minus I star, because the driving force is Y star minus Y. So that's why that time driving force was Y I minus Y. That's why it was YI beam. Now it is Y star minus Y. So that's why Y star beam. Accordingly, this will be the expression, and this is called HTOG, this term, the height of overall gas phase transfer units, H2G, and this is NTOG, number of overall gas phase transfer units. So HTG, HTL, HTOG, whatever you are writing, so according to it will come. Okay, so now some interesting observations. Packed bed mass transfer data for a given liquid gas liquid systems are often reported in terms of height of a transfer unit. For example, for a gas liquid system, HTU depends upon the type of packing material of the gas and liquid flow rate. That's what I am telling. Okay. That's the HTU data on typical system may be obtained from the manufacturer of the particular packing material, because HTOG, but HTG, whatever it is the gas flow rate, and KY, this from manufacturer you will get this. HTU indicates inversely the relative ease with which a given packing can be accomplished separation for a particular system. For a good packing, more specific interaction area. Okay, if more specific interfacial area is there, that is good packing, the value of H2 will be less. That's why I was telling. The packed height required for a specified degree of separation is smaller. Number of transfer unit NTU, okay, NTU, sometimes it is called NTG. If you see this one, just I'll tell you. So NTG, HTG, NTG, sometimes it is called height of a transfer unit gas phase, number of transfer unit gas phase. So sometimes in some book it is written in this way, and in some book it is written in this way. So but you should understand both are equal. Height of transfer unit based on gas phase, number of transfer unit based on gas phase. Height of transfer unit HT. Sometimes it is written this way and sometimes, but it is the same. That is the HT, HTU and NTU. For other thing also it is coming. The number of transfer unit indicates the difficulty of separation. The greater the extent of separation desired, less will be the driving force available, particularly near the top of the column in the case of absorption, and near bottom of the column for the gas. So number of transfer unit, it will keep, if you see that overall expression of HTU and NTU. So this is the expression. So what is this? If driving force Y minus YI, okay, that's mean based on gas phase, HTG, the DNB means diffusion of A through non-diffusing B. G dash K dash Y 1 minus IM, and equimolar counter deficient, that will be this one, and number of transfer unit will be this. If it is based on overall mass transfer coefficient gas, then this will be expression for diffusion of A through non-diffusion B, and this is for equimolar curve, that height of the transfer unit, and number of transfer unit will be this. Now if you make it mole ratio, you can do this way also. Mole ratio H2OG, then G dash S KY, capital K capital Y A, and this will be same, and the number of transfer unit will be this. If it is a liquid phase, similarly for liquid phase, xi minus x, this is the driving force. So then HTL is the symbol, and for diffusion of A through non-diffusing B, this is the nomenclature, this is the expression, and this is for equivalent, and number of transfer unit is this. And when it is x star minus s in some mole fraction, then this will be the expression for height of transfer unit, this is number. And if it is if you calculate this thing in terms of mole ratio, you can make this that calculation also. You can make this mole ratio. What I made this calculation, based on mole fraction. But if you calculate the mole ratio, okay, in this way, and capital Ky in this way, then you will see, you will end up with this easy equation, because that time GS will not change. So that will be G. If you understand what I am telling. So if you take in terms of mole ratio, then what will happen? That will be G dash S into capital Y. Okay. Now if you change this one, G dash S capital Y, then this differential thing, then that will be only G dash S dy. This term will not be there. Okay. So then, that 1 minus Y term, that term won't be there. You do this. If you do this, if you redo this thing, you calculate, you will end up with this equation. This equation. Okay. So, so here, what we have seen, we have seen the how to calculate the height of a pack tower. So height of a cap tower, to calculate height of a pack tower, you have to take that one differential mass balance, then you have to integrate, because this is a continuous process. Packed column is continuous, and based on different phases, different driving forces, there will be different expression of height. And total height, it can be divided into two parts: height of a transfer unit and number of transfer unit. And height of transfer unit, it depends on the mainly that packing interfacial area available. And if inter more interfacial area is available, height of a transfer unit will be less, and number of transfer unit will be generally high when you need the better separation. You need better separation means you need the more purity. More purity, you have to go near to the equilibrium, and that time driving force will be there. So let us stop today. Next day we'll see some simplified form of this determination of the height. Thank you and have a nice day.